So good morning, and I'm going to start then with an example I started but did not finish last class, which is for the Icono equation. So remember, the Icono equation, which is a nonlinear equation okay, and why am I using, we can use any notation. Yeah, it's feasible. What I'm using, see, we can think, let me write a little more. We can think of this as the phase for the geometrical optics wave problem we saw, last class. Okay, so that means we have a variable medium, variable speed medium, okay, wave problem. With variable speed, another word that I use a lot in my research is heterogeneous medium. That means properties of the medium change spatially, right? Many problems arise like that. And geometrical optics, one example we saw this was that Mahmouzi problem of the laptop class images last time. Okay, so now, but we're going to now solve this in forgetting, for the time being, it's good to have the applications in the mind, but forgetting what application we're doing, we're now just going to use our machinery of method of characteristics for a nonlinear problem. Okay, Cauchy data. Yeah, this is the data, okay, which means, I can put the figure here so that I can keep everything together. X, Y, okay, we have this as our sort of what I call initial curve, which is a straight line, and we have the phase varying along this line, okay. Now, in this problem, y is not time. Y is space. Okay, so remember that this wave problem was a two-dimensional wave equation where a 2D medium, the speed varied, and the wave fronts can deform. Excuse me, in the first problem we're going to see, we're actually going to have the solution with a constant index of refraction using the names from optics, even though the problem can be acoustics or water waves, doesn't matter. We can usually use the jargon, right? As I mentioned to in atmospheric flows, sometimes people mention shallow water equations, even though it's air. It would be shallow atmosphere equations, right? So we use the jargon that's sort of established, no big deal. It's basically a long wave model. Okay, here it's not the case. So x and y are spatial variables, and we want to solve this problem. Okay, so this was sort of an introductory remarks for us to remember. Let me quickly go through what we did last class. So we have here, we have to look at the strip condition, because we need sort of Cauchy data to complete our data. From the Cauchy get data for P and Q, right? Because we have 5 characteristic equations now. Okay, so strip condition, very quickly, right? I did last time. So let me write this here in the way we did. Oops. And the notation, okay, was like this. And this is equal to 0. And look, I'm going to do it very quickly because I'm repeating from last class. This one, because the way the Icono equation is written, this one you can say, okay, let's parameterize, put a theta, which we're going to see that we're going to, at the end, have an ambiguity of two possible thetas. Who cares? And actually, physically, you see it's okay. We would need more information to decide which theta we're going to choose. What am I talking about? I'm talking about that I can say that P is cosine theta, Q is n sine theta, and I'm done with this. I don't have to worry about this anymore. So I choose this parametrization because then I'm done with the initial PDE. Okay, now I have to deal with this condition here. So this gives me this, and this gives me that A is, or P plus Q is equal to A, okay? And we'll use this in the future. Let me put it like this just because it doesn't really matter, right? The A comes from here. Okay, so we live with this. Let's keep on going. Let's see how much we can do, okay? And we get, so I did this last time, and I did it almost as fast as I'm doing it now. Doesn't matter because it's really just playing with relations. And as I said to you, when I do things fast and skipping, there's details in the notes, and it's a little bit like an exercise you can do on your own without having to hand it in. Right? So this is equal to A over N. And here's already an interesting, this trigonometric simple relation, okay? By substituting things, blah, 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 already tells me something interesting and physically relevant, which is a little bit this thing here, which is in my Cauchy data, I cannot put this A as I wish, right? Mathematically I could, but as I wish, because if I put A too big, right, I have to put this square root over here, blah, blah, blah. If I put A too big, this sign will not be real. It will be complex variable, complex valued. And I don't want that. I want real valued solutions. And what does that mean, physically speaking? That means if I do this, when this trigonometric relation complains that, hey, I'm going to be complex valued if you put this too large, is what I'm saying is that I'm saying that the phase is varying very fast in S, which is incompatible with the index of refraction. And let me recall to you, maybe you don't remember, the index of refraction is this. And if it's a constant medium, it's saying that things are varying too fast or too slow, which means the spreading, right, is not good. Okay. So now, the last thing is I remember that we did, okay, one thing I didn't do, I just saw here in the notes, but let me just say the last thing I did last class was, so I want to use this board, so let me again separate like this so whoever is, for you, see it sort of changing a little bit the comment. So the first one is this, which I did not mention last time, is that an example, if I put, if A over N is equal to 1, this implies that theta is 0 or theta is pi over 2. Okay? This is, right now, just a trigonometric fact. At the end of the exercise, you will see what this means. Okay? But for now, what it means, this trigonometric fact, is that, look, from my choice of parametrization, and if A is equal to exactly to the index of refraction, okay, theta has to be either 0 or pi over 2. Okay, no big deal. So it's going to be one or the other. You see a little bit where sort of what this means at the end. Okay, this ambiguity. And then we also saw the condition for gamma non-characteristic, okay? And this was, I just put the result here, came out to be this, which comes from that Jacobian, no big deal. Okay, which also mentioned that two thetas that cannot be acceptable. So fill in the details, parts is in the notes, and it's easy to do. And then, okay, another thing I did too, I'll repeat part of it because I think it's good, it's intuitive, is looking at the Monge cones that appear from here, that I mentioned at the very end of the class about light cones, right? So let me do it again. I like it, so maybe I'm doing it again just because I like it, but I think it's because it's good in terms of intuition, right? But it's good because I think I went a little too fast. Because it was the end of the class, and I wanted to prepare for today. So PDE, right? The PDE I can write like this. Doesn't matter. Equal to 1. We have the P cosines, whatever. So what maybe I did a little too fast last class, but it wasn't because I knew I was going to repeat it, is that look, I don't even have to put information here. We're just drawing like this, gives me like a circle of radius n, right? Okay, and therefore, what I did last class, a little bit fast, but not, I mean, I don't think it was too fast that you could not understand, of course. And what I did is this, look. If I come down -1, and I have here a radius of n, right? What am I doing? Right? I'm on purpose not saying everything for this. Sorry? Isso. That's right. So the normal, exactly. So, exactly. So the -1 here is already indicating the last component of the normal. So it's PQ -1 is a normal. So these guys, these colorful arrows are the normals, okay? So let me put it like this then. Yellow normal, orange normal, okay? So normal to what? To a plane, a tangent plane, right? So this I did last time, and then I went a little too fast, but it doesn't matter. So this is like normal. And put it like that. This is like normal. Like this. Okay. Let me make it like that. And therefore, here I have a cone with the normals, right? This looks already like a cone, but actually here I have a cone. So this is a tangent plane, right, for that normal and so on. Okay, so therefore, this, I think I wrote this last time. This is a Monge cone. Okay, and one thing I didn't do, and I think it's good for us to do, and I think I can use this figure here, is this. So look, let me see if I use the yellow. Let me use the yellow guy. Okay, So this is 1, right? Because this minus 1, let me erase it. Let me erase this n. This is n. Let me call this angle here alpha. So I have that tangent alpha is equal to n. Please, I'm sorry a little bit about the notation, but there's n and vector n, right? N is index of refraction, right? There's no way to fix it. I'll just make sure whenever I talk about the normal, I'll put the vector sign. So tangent alpha is is equal to n. And then check for yourself. It's just trigonometry, okay? So it's simple. So look, if this is alpha, 90, so this is 90 minus alpha. Right? And therefore, you can see that more or less if this is 1, this is 1 over n. Okay? So this is interesting because it says the following. Let me maybe make my hands free. Is that depending on the index of refraction, the cone opens more or less, the light cone. And remember this. I also mentioned this, I think, fast last time, that if I put this in an application, this is a level curve for a phase, and we can think maybe in some case it's a little bit like a wavefront. I'm actually going to talk about plane waves in the plane wavefront. So if I put this is a level curve. Let me get the red one. This is another level curve as I slice it like that, which is okay. And for this, if I look from above, I'm going to see something. Which one did I use? Yeah, white. Red, which I hope in the video it appears as red. And if I put here, sort of a blue, if I slice it, right? So these are the wavefronts, right? And if I have, this is like the case of dropping a stone, say, in water, and you see circular wavefronts, right? And the phase is, as I remember too, the phase is, for example, if I put 2 pi, multiples of 2 pi, which means for the real part of the e to the I, blah, 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 I see just the crests of cosine-looking guys, right? You can visualize that, right? Look, seen from the airplane, you drop the stone. Okay, so therefore, I missed a little bit part of the story I want to say. Okay, wavefront, okay. And yeah, and the Monge cone, because we're using geometrical optics here, it's a little bit, we can call it, and I mentioned about time-like, space-like things we're going to see in the future, it's called the light cone, because it's how a point, a source, if I drop the stone, how it affects, or if it's like a little flashlight, right, how it affects, it illuminates the medium. So the word illuminates in many applications appears just as a means of activating something, right? I mean, the solution not being non-zero. I once heard a very interesting part of a talk of somebody who studied the brain and would say, oh, when you see something, you illuminate a certain part of the brain, because in the sort of tomography or whatever you see that part being activated. When you speak, it's another one, right? And very fascinating things, including because he said that when we hear something, we activate a part of our brain. When we see something, we activate another part of the brain. But actually, if somebody is deaf, right, doesn't hear, but sees the signs, it activates the same parts as when we listen. It's many interesting things. I'm not experienced in that. But the word illuminates, right, if I use it again here, it means sort of activates, right? So, okay. All right. So I want to talk about the Monge cone. Now let's solve our problem, okay? Now let's solve our problem for the Cauchy data we have, okay? Here I'm just seeing something at a point. And then I'm going to solve with the Cauchy data at a point. We're going to get this guy. Well, we'll get to that in a second. Still today. So characteristic equations. Characteristic ODEs, Sharp-Pitts equations. We have dx, d tau. Let me copy here so we move fast. Two p squared plus q squared. This is our system of ODEs. Again, as we saw with Berger's equation, check them, take a look quickly, because sometimes here at the bottom there's useful information, things that are not changing. For P and Q are not changing, so that makes these ODEs very easy to solve, because they're like constants, right, along the characteristics, the orbits. Okay, so let me write the answer. It's easy to integrate. Well, let me just, for the first one, let me write like this. So S, let me put with the full notation that I'm using here, just so that it's good, right, for pedagogical reasons, right? So this means just the initial condition for this ODE, which is the Cauchy data. This is a constant. Integrating is very simple, right? So when you put the long notation, it looks almost like it gets more complicated. No, just so that all the information is there, but it's super simple, right? And then, so the second one, we're going to get that S plus 2, I'm writing the same way I have it in the notes, is equal to Y. And this one, I get that Z is going to be equal. I'm skipping some calculations, okay? So just that we don't have to spend time with details, and then I can even make little silly mistakes on the calculation. It doesn't really help much. So we have this. Okay. And here, well, let me complete here. X is equal to S plus 2n tau cosine. So we have all these guys. Inversion is, right? Don't even have to mention that. Multiversion. And, okay, we solve this. For tau and S, very simple in this case, right? I'm skipping some points. Again, these are good exercise. Do it without looking, and then check if you get. And then we get at this. So, you know, people who are watching this video, right, should do this as exercise. After manipulations, we get that okay? So sometimes it's good to see if you didn't, to see if you didn't do any mistake, check that satisfies Cauchy data, and check that satisfies PD, Icono equation. Okay? To check that it satisfies the Icono equation is super simple. To check that it satisfies Cauchy data is also simple, but it's basically satisfying, substituting, everything and blah, blah, blah. And you see the relations that are on the other board, all in terms of S, will come together and say, yeah, it satisfies. Okay? Very simple. So what does this tell us? So the question now is, right? I solved this problem, which is not quite just memorizing things, which is bad to memorize things, kind of understanding, right? I mean, all the equations of the Sharp-Pitts equation, the characteristic equations, particularly the last few ones, sometimes I have to look to check the signs and so on, so I don't get it wrong, right? The vector field of dp and dq, d tau. And then, okay, I solve it. We manipulate it. And we get to this. So if I'm thinking about a wave problem, because I can be solving the Icono equation, just as the Icono equation is some nonlinear problem, right? But no, this is an applications in PDE's course. So look at this. Maybe it's so simple, maybe I'm puzzling you just by asking what you have to say. Isn't this telling me that basically I have a plane wave solution? Remember last class, right? Remember that to get to this solution, we did an ansatz that had a guy, that had a term that was something like that, right? And that's why this was the phase. Maybe there was a k here outside, it doesn't matter, right? But it was something like that. And of course, that's why I put this equal to a constant. I get, this is my phase function. It says where e to the I 2 pi is, and so and so. And then, from this last class, go back and look. I'm not going to write it here. I showed you what a plane wave is. Okay? So let me draw something. Well, plane wave is like this. Let me draw it maybe like this. If we see from an airplane something like that, it's usually because the wave looks like this, right? So this yellow line here, my drawing is not 100% perfect, right? But it's at the maximum, right? The crest. And then if this goes down and up again, down and up again, down and up again, I can actually, if I wanted to put another line here, which is the trough, and here's another line here, say, for the crest. Right? This is for a different phase. And these are for, right, the maximums, but with a phase shift, right? With a phase difference. So this, right, go back last class, we showed this called like a plane wave for many reasons. First is a wave that doesn't vary in this lateral direction. So it's like, that's what. Plus, this looks like a plane. We'll go back to the next class, last class, and we'll see that this vector here, we did this in the last class, is the vector k, which points the direction of which my wave is going, right? This is a plane wave. And of course, if the wave is sometimes, which in the ocean, you see it comes and it sort of adjusts to become a little more parallel to the beach, that means that the vector k is changing, right? And that's all sort of built in to the phase function, and actually the fact that the phase function, the gradient of phase function, right, has to do with the case. We're going to see this in a little while. Well, what I'm saying now is just words in the air because I'm not showing you. So don't worry about that. But what you should understand, and yes, worry if you're not following 100%, is go back to the last class, right? We have it on video, we have it on notes, is that this looks like a plane. This is like an inner product of k times x, right? The vector k times the vector x. That's how I did last time, okay? And we have this picture in our minds. Okay, so therefore, for the constant index of refraction, right? Because n here was constant, we have a plane wave, right? Which means here, right, sort of, you have these guys like this, and check. Well, I have here in the notes. Okay, well, to be complete, let me put it here. Let me stay on this blackboard because then I will start something new over there. So what I put in the notes in one of the pages, which I'm not sure if this page, because I call it 33A, I'm not sure if I scanned it. It's a little bit just a reminder for me to tell you, and then you do it a little bit as an exercise too, is that if, an example, if A is equal to N is equal to 1, we have this. So convince yourselves of this. Let me put here my Cauchy, the curve where I had the Cauchy data, and we have two possibilities. Waves like this, or waves like this, okay? Because in this case, let me put here, theta equal to 0 or pi over 2. We already did that. Those are our two options. So, right? So convince yourself of that. And then I put another A. So if you have another A, these angles change, okay? Right? Because what does the A says? The A says, here it is, the A says how the phase is varying along this line, right? And of course, depending on how it changes, right, it moves fast or slower, it has to do with these angles here, okay? So exercise number 1 for you, not to hand in, do it your own, is that if I live, which is fine, with this ambiguity of my parametrization that theta is 0 or pi over 2 because A is equal to N is equal to 1, then I would need one more piece of information, which I don't have, which says that my wave fronts are either going along the x direction like this or along the y direction like that. Right? I don't have more information to choose between these two possibilities, which are good. Okay? If this guy changes, these angles change a little bit. Okay? So that's all there is to it. And okay, I'm fine with this, with the information I have. I cannot decide between which of these two wave fronts, right, seen from the airplane, like this or like that, is the one that is the solution here. Okay, so that's the story from the Icono equation with applications. And now let me do just one more case of the Icono equation, because then, it's interesting. You'll see. And it's a singular case. You'll see. I'm going to basically get the same things, right? So now, another example. And of course, I don't have to do all the details because it's very similar. So solve now the Icono equation where the Cauchy data with the following, let me write down everything. With the following singular data at a point. Okay, so it's singular data. It's a little funny looking, but let's try to deal with it. And later on, I'll mention to you how we can use this. I won't mention today. So strip condition. At first, this is going to be 0. Has to be 0. But of course, and the other one is this one. This is 0, 0, 0. So this one's kind of satisfied. And this one just gives us, I'm going to put it here, same theta parametrization, okay? And then, here, as a little bit like an exercise for you, details in the notes, so don't look at the notes. So we have same characteristic ODEs, but now the data is a little different, okay? And so let me put it here, solve to get that. Okay, solving the same characteristics, but now it's slightly, the data is that guy, the singular data, this guy, the singular data. Substitute, eliminate the variables, and to get this. Okay, or even better, this. Which is basically, I'm going to call it the okay, drawing very quickly in a way, sketchy way, a little bit on purpose. So you have to make sure you understand, fill in the details. Okay, so basically, it's almost like the same thing with this funny looking data, which is only at a point, not at a curve. Well, let me see. Okay, I can deal with it. Solve the ODEs, substitute S tau, get rid of it. You come to this. It's better to write it like this because it looks like a cone and so on. And we get exactly something that looked as our light cone now at, right, x0, y0, z0, right? This is sort of the level z0, right? Which is, so basically the singular solution, it's singular because for many ways it's a little funny because it's only at a point in terms of Cauchy data. It's singular also because if I differentiate, right, at the point, for example, look at here, differentiate dz, the square root doesn't have a derivative there, blah, blah. But it gives us what we did from another means, which is a little bit the light cone, the way sort of things illuminate the medium, okay? And then I'm going to show it to you or give it to you to do is how to use this to sort of use this to go back to that solution. Okay? We'll see this. Okay. Good. Good. So now let me mention some applications again and go to systems. Okay? So I went a little sketchy here and there, but it's no big deal because I'm skipping just algebra substitutions and things that you should do on your own and pretending you don't know the details as like an exercise to warm up.
Você sempre acha monte de hipóteses você botar essas condições iniciais até ou isso é só dessa equação aí?
Well, here, I'll answer in English because of the video, okay? So here, you get the Munchkin doing at a point. I think if you can solve, I want to say something that's wrong because I don't have all the equations in my head, but if you're able to solve something at a point, you should, let me put it this way, okay? That I know I'll give you an honest answer without having the whole possibilities in my mind. What I just did here, and in some cases you might do it this way or another way, is to understand the region of influence of that point, right? We did that before through other means, right? For a wafer. So this is basically what I'm doing, okay? Finding sometimes, so I don't want to give a complete generic answer because I might be missing more complicated problems and we're talking nonlinear problems. But this, what I just did, is one way of finding the region of influence of that point, right? And that's good, right? We want to see that good, in particular in problems like hyperbolic problems and so on, so problems where we have this sort of a region of influence which is sort of limited, right? We're going to see in the elliptic problem that instantaneously everything feels everything when we do Laplace's equation. Here there's actually no time, but still there's this thing. At one point, I think at the end of the course, if I have time, I'll do problems higher dimensions, spherical means, and so on, and we see things like that too, regions of influence. Okay? Good question, and forced me to put it in a different way, which is this. See it as a region of influence, which here has a special name, the light cone. Nice name, okay? Okay, systems. Hyperbolic systems. Let me give two examples before explaining, right? Two examples, and let me put it like here. Of interest, well, there are many examples of interest, but here because are examples that I kind of showed to you in the laptop, the picture sort of class that I gave, okay? So two examples. And 2x2 cases. Look at this. Let me mention the first one. The first one, you already saw it in my slides. Let me put this here maybe on top. These are acoustic waves, okay, where u is velocity or speed, p is pressure, okay. Maybe I should have put like z of t, p of zt, rho of z, or constant, right, is density, and 1 over kappa is compressibility. Okay, so this is like the problem. If you can put the z up or down, doesn't matter. Let me put it z maybe sometimes down. remember the problem of waves in the crust of the Earth, 1D waves in the crust of the Earth. Okay, the Z could be up or down depending on how you choose things. So think of this, as I mentioned to you, as a bunch of matrices. That's the way I think of it, right? A bunch of like matrices, one on top of the other, with different densities and compressibility. Okay, which means compressibility, right? Kappa, or capital K, is bulk modulus, something has to do with elastic properties of the medium, therefore compressibility. Rho is the density, right? So that has to do with its sand, clay, rock, what type of rock. So the propagation speed is different. You're going to see the propagation speed coming in soon, which is C of Z is 1 over square root of, sometimes I get it wrong, kappa over rho. Okay, and in the case of the crust of the Earth, a layered medium is a good model, right? We see this when we see the cut of a mountain, particularly Grand Canyon is a perfect thing. You see very colorful striped things. And this problem becomes very complicated if you think, well, the speed is piecewise constant. That's not so bad. We'll see how to deal with discontinuous coefficients later on. But then there's these problems that Papanicolaou and collaborators did where you think of this with uncertainty. You put random coefficients on. It gets very complicated. I showed you some things. This is beyond the scope of the course, but at some points I might mention some things around this, okay? Now, let's think, if we want, we can think also of rho and kappa as constants. It's a homogeneous medium that doesn't change properties. Just a big, huge mattress, right? I jump on top of it. There's a pressure wave that goes down and just keeps on going down. If there's a change, just one change of material, we're going to do some cases. This I'll show you later on in the course. If I have like two big matrices, when I go from one case to the other, there's reflection, right? It's like here I mentioned the echo. If I start shouting, hey, maybe somebody in this auditorium will hear a little bit of the hey, which is the transmitted wave. And of course here, because in auditorium we don't have echo because of the scenario, but if you have echo, that's the transmitted wave, the reflected wave, okay? So we're going to start learning step by step some of these things that I'm mentioning here in words, right? So I'll tell you in a second why this is a hyperbolic system. You don't know yet what that means, okay? But it's a 2-by-2 system, right? And I can write this in matrix form, okay? So one example, let me write this in matrix form. I can write this like this, look. So UT is equal to rho and PT is equal to, okay? So if I did everything right, this is written in matrix form. No, here would be kappa. So I wrote this wrong. If I make a mistake, help me, okay? Now it's right, right? Right? Okay. Now, we're going to see that actually a system is hyperbolic if the eigenvalues of this matrix are real and the matrix is diagonalizable, which means the real eigenvalues are propagation speeds. And here you're going to see that actually here the eigenvalues is easy to see. It's plus or minus this. So since it's plus or minus this, or I can put it here, it means I can have waves going this way or that way with that speed. Okay? If the medium changes, if the property changes, the propagation speed changes. Okay. So this is one problem, acoustic waves, propagation speed. Oh, so okay, I have to mention this, which might be confusing at the beginning. It's good that I look at my notes because it reminds me things. This is important. Wave propagation speed. where this other speed or velocity here is, you know, think of two things. Let's think of the mattress again, right? If I jump on the mattress, there's a speed of something going up and down in the mattress, right? But there's a pressure wave that keeps on going down. So don't get confused about these two speeds, right? This is the speed of like a particle of the mattress going up and down as I can. And this speed is of propagation speed. It's the wave that keeps on going down from mattress to mattress to mattress. The transmitted wave, there's the reflected wave. And of course, in a reflection transmission problem, right, this is not constant. I mean, I'll come back with, but this is a little bit some of the things I showed in those pictures I showed to you of like apparent diffusion, this and that, right? We don't have enough information here to discuss this in an intelligent way. That's why I'm just talking like this, okay? Just like information, a little bit disconnected for the time being. There's a similar problem to this, which actually, right, was helpful to me since I was doing water waves. So let me write this problem here. Okay, where u of xt is also speed or velocity, right? Eta is wave elevation, or I can also think of this as connected. No, let me not write this. I will just mention it's really. Let me do a figure or dimension. And g of x, no, not g of x, c of x, which is g square root of h of x. This is the wave propagation speed. And what kind of problem is this one? This is this problem like this. So this is shallow water equations. Or a long wave model, okay, where this means that this lambda is much bigger than the average depth or the reference depth. So that's why it's called a long wave model, because like tsunamis is a long wave model. Okay, this is the simplest probably model for a long wave model with a variable topography, which means the depth is varying. How this comes into the equation? Here, the depth is varying, right? You can change this model, as I indicate. You can, because of this variable coefficient here, you can call this maybe psi, which is a little bit like a flux. See, this is, u is a horizontal speed, right? So it's a horizontal speed like this of the wave of the water particles. So here, 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 the water flux over the column depends on the height. So if you call this psi, you can then multiply this by h and write this as psi, okay? Then you're going to have a gh here, and when you compute the eigenvalues, you get the speed, okay? I'm just pointing out things too. Again, little manipulations you can do in your own time, criticizing everything I say, which are then several mini exercises on your own during your studying, the time you're studying all this, right? Now, look at this. This acoustic problem has, from a mathematical point of view, some similarities with this problem. Okay? One thing I was going to write here, and I pulled myself back, is now I'll explain is that, look, the wave height, which maybe, let's put this part here, right? So this is the wave height, right? It's also, I can also think in the fluids class, we learn this. Here we'll not learn this. But it's the excess, we call it sometimes G times eta, the excess pressure due to the wave. What does that mean? Or the excess hydrostatic pressure of the wave. Hydrostatic pressure, so mini fluids course here. Hydrostatic pressure, the name says, it's the pressure. Hydrostatic means of something that's not moving, right? So if I put a column of water here, water is heavy, right? So it makes pressure on the ground, right? A meter by a meter by a meter is a ton, right? Weighs a lot. So this is the excess pressure for the undisturbed water level, right? So if there's no waves, everything is calm. Of course, there is pressure. But when the wave comes, there's an excess pressure, right? So the wave height, eta, is connected to the excess pressure. And look at this. So we have speed, pressure, excess pressure. So a little bit of an analogy, physical similarities of two models that are very different from the physical point of view. But more importantly than that is that mathematically, they're very similar. Mathematically, it's a hyperbolic system with a propagation speed, which is the eigenvalue here is plus or minus lambda, which means wave going that way or this way for the homogeneous medium is the same. Here is the same thing. Propagation speed is plus or minus this, where when, if you think of h being flat bottom, constant depth, the speed is plus or minus to whatever direction, okay? This is a very simple model for water waves, right? It's not nonlinear, so it's very, say if you think about tsunami, it's kind of okay in the beginning, but when it gets to the shore and the wave might start breaking and so on, it doesn't work. But mathematically they're similar, and that's a little bit why, and you see this more later on, why at one point I mentioned this in the lecture with all the slides, that with some colleagues we were able to import technology from acoustic waves with the random coefficients to water waves with a random topography. So you can start believing a little bit why, because mathematically they look the same, and so certain technologies, certain theorems, we could bring them from the acoustic case and basically use those theorems just by adapting the model so that we can make the analogy. Oh, this in the acoustics means this. So that's a nice thing about mathematical modeling, because sometimes you can jump from one thing to the other because the mathematics is similar, of course. Always talking to somebody who is an expert on the other field, which you're not, to make sure you're not making a hypothetical mistake, right? Something that's... But sometimes you can make something that's unphysical just to understand the mathematical technology, but you have to know you're making something unphysical, right? Unphysical in the sense, oh, this hypothesis is not really seen in the nature, but it's useful for me to check the theorem or this or the computations.
É só para onda rasa, isso daí?
Ou onda longa, or long waves. Okay, so this one...
Tá, eu digo profunda não, né?
No, because you see, you're asking about if it's good for deep waters. It's good only for deep waters if the wave is longer than the depth. Okay? I'll show you a model in a few classes which is more general than this, and then it sort of fits more generic situations. Okay? So when I say shallow water or long wave model, it means the same. And long or shallow is something with respect to something else. So if you think, oh, deep water because it's 4,000 meters, that's for the tsunami. Well, I say, well, it's deep for us, but it's not deep for a tsunami, which is 1 kilometer long. Right? So always have that in mind.
É que eu estava pensando em usar esse modelo para inferir a profundidade. Do mesmo jeito que a gente infere as camadas de uma rocha utilizando a propagação, né, de uma sísmica, por exemplo, inferir a geologia da subsuperfície marinha.
There are some models. It's not easy, but using potential theory, not this model, the slightly more complicated one. I mean, not slightly more complicated one, but we're going to see in this course, which mixes Laplace's equation with waves, where there are some problems. There are some papers. Who knows? Maybe could be a paper for you guys to review in the future, where there is an inversion using what you mentioned, and so that people know what we're talking about. Is like using the waveform to infer what is the depth variations in the bottom. Okay, it's not an easy problem, but it can be done, but not with this model, with something a little more sophisticated. Okay, so good question. Makes sense, but not with this model. It's too simple.
Só uma última. Isso aí vem de Bernoulli, né? Provavelmente. Essas equações vêm da conservação de energia, aquela lei.
Yeah, well, this eventually comes from Bernoulli. You also will see this, okay? So this is a good question. So what's being asked is, where do these equations come? Does it come from Bernoulli condition and so on? It's not, since this is not a fluids course, I will not tell you how we get the Bernoulli equation, but I'll give it to you, the potential theory with the Bernoulli equations, with this and that, and we will learn, which I mentioned to you, which is the asymptotic analysis of differential operators, how to get something very complicated that comes from Euler's equations. Right? In fluids, those two equations that are very famous, Navier-Stokes and Euler. And how you get Euler equations, which are very difficult and so on, and you start simplifying it in a sort of educated mathematical way. Educated, I mean by systematic. And from that equation, from Euler's equation, you can deduce many, many different, depending on the regime, many, many different famous PD systems. KdV, which is not a system, a single equation. Boussinesq, you can even deduce Schrödinger equation, right? And if you deduce Boussinesq equation, which is a weakly nonlinear, weakly dispersive equation, and I'm going to get to his question, is that you still have to understand what I mean by weakly nonlinear and weakly dispersive. You will understand soon. But then I say, okay, forget, it's not a dispersive. It's not in the dispersive case. So switch off the dispersion part. Oh, it's not weakly nonlinear. It's linear. Switch off the nonlinearity. What do you get? You get this. So this is like the ultimate simplification of this hierarchy of simplifications that we can do. You will see this kind of soon. I don't know, 2 or 3 weeks. Okay, I don't have the timing in my head. Okay? Very good. Okay, so let me go over there. I have some time. Let's do now write things in an abstract form, meaning forget about acoustic waves, forget about water waves. Let's write a system in a more generic form, right? A linear system in a generic form, forgetting about the application, so we can see the eigenvalues coming in, blah, blah, all this thing I'm talking about. This was like a motivation, okay? So consider this. So if I just write this on the blackboard, can you sort of already anticipate which kind of problem I'm talking about? I mean, not even anticipate. Say in words. I have a system, right? Because it's not my solution. Why I have a system? Because I don't have only one equation here. I have n equations here. capital N equations. Okay, the notation is short. So, therefore I have a system, because all these components, they might be related. So I'll mention to you what does it mean. Sort of at some point we can actually diagonalize the system and actually decouple the components. Here the components in principle are coupled. That means the dynamics of one component interferes in the dynamics of all other components or many other components. So that's what I mean by coupled. So if I didn't explain to you just writing this, I think you can understand the notation. Look at this. If this is a vector, right, a column vector with all my components, right? And as you will see, some cases, all the components do not have to be, the notation is U, which is the notation I use for speed, but does not have to be speed. It's just because it's a vector U, right? Over there was pressure. So U1 could be U, and U2 would be P, and that's it, right? So what I'm saying is almost pedantic, simple, but just to make sure. So A is a matrix. And D is a vector, right? I use capital letters, doesn't matter. So, right, so I have a system of n equations. Matrix times vector is a vector, 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 and therefore this is a vector, right? This is like a independent forcing term, if you like, right? That could change in time, in space, okay? All right. And let's talk now about the Cauchy problem for this guy. Cauchy problem. Along, let me write it like this, like the Cauchy curve, right? The curve. Okay, which means, so see, things look like they're getting like super complicated at once. It's not. First of all, this problem is linear. Right? The problem is not even quasi-linear. The problem is linear. Right? Let's start with this problem, linear, simple. The problem is linear. Looks like a system, any equation. No, we know this. I could go away and let you study by yourself. This would be easy. The problem is linear, okay? It is two independent variables, which would be like x and y. Y is here explicitly time, okay? So I can draw this. Okay? Where now I have to keep track in my mind, no big deal, of like n different, capital N, different pictures like this. Because Z, let me put it like this, it's just like Uj. Right? For every component, I have like, if I solve it, it's like my integral surface, blah, blah, all the same. Okay? And here, my Cauchy problem, if this is T equal to phi of x, right? My drawing in the notes was like this. I have the initial information for this guy. So actually the proper way to write it is this, right? What I just drew over there has to do with this. So see if you agree with me. I mean, there's no big deal. There's no new concept. There's nothing complicated. Just more work of housekeeping, right? Organização, just housekeeping. Because this is my Cauchy data, Cauchy problem. This is the Cauchy data, which says that the vector u along this curve is given by this vector, right? So I get each component of f. And basically draw here. So I have basically n copies of this, right? And if I solve for all my components, I'll have an integral surface for all these guys. The complicated thing is not only the bookkeeping of notation, but it's that this 3D picture is connected to another 3D picture here, which is the other component, connected to another 3D picture there, and they're all influencing the others because these matrices here are not diagonal. They couple the guys. Right? So no big deal. Right? I mean, just looks bigger, more complicated the problem. It's just bigger. Right? More things to keep track. Okay? So, let's go and use the ideas we've been seeing. Strip condition. How do I write strip condition for this guy that's just bigger than the others? Not more complicated, it's just bigger. And it's linear. Well, strip condition is going to be the initial PDE and that condition about orthogonality, blah, blah, blah. So initial PDE is this. And the other condition is this. Do you agree? Look, right? Let me make sure. I don't want to, right, get you just puzzled because of notation. And there's no new concept. This is just the initial PDE. Strip condition is the initial PDE, and which is this. I'm just omitting this, right? Of course, it's evaluated on the curve. Evaluated on the curve. This is the initial PDE, and this is just basically that du dx is equal to 0 because my parameterization now is x. Right? Remember that it was du ds before. Who cares? Now I don't even need the s. Now I just go straight with the x instead of s. Boom, this is this. Okay? And this, you know, just so you see, I think this is just the analog of this. I mean, it's not the analog, it is this. Component, right? This is for every component, right? If you look at this, there's n conditions hidden in here because it's a vector, not hidden, right? There's n conditions, right? If you do component, this is of course equal to 1 because it's a parameterization. So this is just that condition we had before. The j just means for each component, okay? But forget about this. This is just so we feel comfortable, right, in reading this. Now, what do I do with this? Let me erase this board. I'm going to need it. Just be a little more organized. So, okay, so let me write this here in a slightly different way. Okay, the problem is linear. I'm going to try to solve. Remember, we have to try to solve, to get things going, we have to try to solve the strip condition, right? And what did we solve the strip condition for? We solved the strip condition to get Cauchy data for P and Q. Fine? For P and Q. Well, but what is P and Q? P is du dx. Q was du dy, and here du dt. Okay? And I told you actually we keep on repeating that, this process of getting other derivatives, which is a little bit of like starting a process to solve the solution by power series, like a Taylor series. Okay? So here, solving the strip condition means being able to solve for u of x and u of t. Before was for P and Q, which are a little bit like these guys. Right? Is it okay? All right. So now, because we have a system and things are more complicated, this is what we're going to do. We would like to get this vector and this vector, right? This is a linear problem. So this one is easy, right? It's not that there's that nonlinear. This is easy. So the strategy is, write, as I did here, u of x equal to that, substitute it in here, and try to solve for u of t. If I solve for u of t, boom, I plug it here, and I get the u of x. That's the strategy. Simple, because the problem is linear, right? In the nonlinear one, we had to get the q as a function of p. Sometimes we could, sometimes we couldn't. Okay, so now if we solve the system, excuse me, substituting u of x in the initial PDE, we get that okay? Which looks a little bit like an ODE, doesn't really matter. But now, we need right? Note that all this is, don't forget that, okay? The notation is hiding that. We all evaluated at Cauchy data, okay? So now I'm trying to get, and this means determinant. So I can solve for this guy, right? This is a matrix. So this is like a, this is a linear system, right? AX equal B. This is all known, right? If this depends on x and t, it's all evaluated at x phi of x, right? This is known. So to solve the system, I need this determinant to be different from 0, okay? So if determinant of A minus is 0, this implies that t equals f of x is what? Characteristic. Very good. Right? I'm not being able to get out of the Cauchy curve, as I say out in the sense of getting out locally, because the curve is characteristic. Okay, so another way of writing this is determinant of A dx minus B dt equals 0, right? Just write in terms of increments, doesn't matter. And then finally, yeah, and good. Now let me go quickly, and I'll refresh this when we come back. But now let me do something very quickly, and then I'll come back to this because of the time. Now, say if A is non-singular, we can sort of normalize our system, or put in normal form, that's better. We can put our system in normal form, writing it like this. You see what I've done? Get this system. Yeah, or, well, not this system. Yeah, could be this system, yeah. Multiply by A minus 1, whatever. It would be the original one, right? Doesn't matter. And then you get this where B tilde, C tilde, all these guys are modified, and not the U tilde. I got the tilde in the wrong place. Right? Sorry. Right, just get this system here, multiply by A minus 1, right? So B tilde is A minus 1B. And now it's a good point for us to stop the lecture, because now this condition here is that determinant of, let me write it like this, so this is the condition to be characteristic. And look at here. The characteristic lines are connected with the eigenvalues. The propagation speeds, you can verify what I did there. The propagation speeds are connected with the eigenvalues. The wave propagation speeds, right? When I say propagation, it's because it's wave, are connected to the eigenvalues. So this is a very good point for us to stop, because I always start my lectures reviewing things. I'll review this, right? But connects very well with that. It was a very good point, as I wanted to stop connecting with the acoustic and the shallow water model, which you can. Now, it's very easy. Compute the eigenvalues and you find what is the tsunami speed, okay? And you want to see the tsunami speed, just maybe as a final comment, excuse me. The tsunami speed here, right, which is this is the eigenvalue of this when you write it in matrix form for this variable here, psi, and I thought it's right. If you compute the tsunami speed when it's a linear wave just in the beginning for a depth of 4,000 meters, and you approximate, I put it like this, the gravity acceleration for 10 meters by second squared, you're going to find out that the propagation of a tsunami, that is the propagation of this hydrostatic disturbance, right? It's not the propagation of the fluid. It's not like the fluid is going like that. It's this guy is the speed of an airplane, 720 kilometers per hour. And that's why when there's a submarine earthquake not too far, say 300 kilometers from the coast, which is far, people panic because if a tsunami is generated, and it's hard to predict, from the earthquake it's hard to predict if there's a tsunami. The earthquake can shake like this, can shake like that. It depends on how it disturbs the free surface. You have half an hour to evacuate certain places because if it's 300 kilometers away and this disturbance goes at 720 kilometers per hour, right? If it's just 100 kilometers away, there's even more, there's less time, right? That's why. And here's how to compute the speed of a tsunami from this linear model, which is pretty much okay for that purpose. Not for the problems we're asking of like inverting the depth. Then other things you need a more sophisticated model. But this speed to leading orders gives you an idea, or at least gives you an order of magnitude, a scary order of magnitude of the speed of a tsunami. Okay? So we finish here. Obrigado.